Good morning. Today we will be discussing about the second part of the second module of CET203 Fluid Mechanics and Hydraulics for the second year civil engineering students of APJ Abdul Kalam University, and we will be studying about, or we will be discussing about the stability of floating bodies and the concept of Metacentre. So what exactly is Metacentre? Metacentre is defined as the point about which a floating body starts oscillating when tilted by a small angle. So here you can see a small floating body partially submerged in water, and if we give it a small angular displacement, it seems to be oscillating, or it will oscillate back and forth, and it seems to be oscillating about a particular point, and this particular point about which it seems as if it is oscillating can be defined as its metacentre. Okay. Now we can also locate metacentre graphically. So metacentre is defined as the point at which the line of action of the force of buoyancy will meet the normal axis of the body when the body is given a small angular displacement. So this is how metacentre can be located graphically. So I'll show you how that is done. So this is the floating body. This is center of gravity of the floating body, and this is the center of buoyancy of the floating body. Weight W is acting through the center of gravity, and buoyant force Fb is acting through center of buoyancy. Now, as you all can recall from the first video on module 2, center of gravity is the point at which the weight of the body seems to be concentrated, and if the body is a uniform body, center of gravity will be at the exact center. Center of buoyancy is located at the center of the submerged portion of the body, and so this is center of buoyancy. Now, if we give this a small angular displacement, now this dotted line that I've drawn here was the initial line that had actually passed through G and B when it was in the horizontal position, and G and B are over here, and this is the tilted normal axis position. So this is known as the normal axis of the body. Now what happens is center of gravity does not shift. Center of gravity remains where it is. Whereas if you look at the center of buoyancy, according to the definition of center of buoyancy is defined as the center of the submerged portion of the body. Now, as you can see here, the submerged portion of the body has changed. Once the angular displacement has been given to it, the submerged portion has been changed. So, center of buoyancy would be shifting to the new center of the submerged portion, that is B dash. Let us call it B dash. So center of buoyancy is now concentrated at B dash. Sorry, buoyant force is now concentrated at the new center of buoyancy B dash. If we now extend the line of action of the buoyant force, it will meet the normal axis at this particular point, and that particular point is known as the metacentre. So if you can read the definition of how to, or if you can read how metacentre is to be located again, it is defined as the point at which the line of action of the force of buoyancy will meet the normal axis of the body when the body is given a small angular displacement. So this is the normal axis of the body, the initial axis where center of gravity and center of buoyancy had lain, and once tilted, this is the normal axis of the body. Center of buoyancy has shifted to B dash, and this is the point at which the buoyant force is acting now, and when we extend it, it will coincide with the normal axis at a particular point, and that particular point can be defined as metacentre M. So now that you know what is metacentre, for us, the thing that is more important than metacentre is metacentric height. Metacentric height is the distance between the metacentre of the body and the center of gravity of the floating body. So here you can see a floating body, and its center of gravity has been shown as well as the metacentre. This is the normal axis of the body, and this distance between M and G is known as the metacentric height, and this metacentric height plays a very important role in deciding the stability of the equilibrium of a body, and this we will be discussing in the later slides. Now, how to determine the metacentric height? There are two different ways in which we can determine the metacentric height. One is an analytical method or a mathematical method where we will be going for pure mathematics to understand the formula for metacentric height. And the second method is an experimental method wherein we would be conducting a small experiment in order to determine the metacentric height. So first let us deal with the analytical method for determination of metacenter. So here what we have shown is a top view of a boat. That is the plan of the boat, and if we take a section cutting through the center of the boat, then this would be section AA of the boat. This would be the sectional view of the boat, and it is this sectional view that we are going to use in the derivation. So this boat is now partially submerged in water, and instead of water, let us just consider partially submerged in a fluid, because metacenter exists for bodies that are partially submerged in any type of fluid. So this is the normal axis of the body, the dotted line, and this is G, center of gravity, that is the center of the total boat, and B is the center of buoyancy, which is the center of the submerged portion of the boat. I have also drawn a yellow dotted line that shows the water surface or a water line on the boat. Now we are going to give it a small angular displacement. Only when we give it a small angular displacement will we be able to notice the metacenter. So once the angular displacement has been given, we can notice the changes here. The yellow line, which was initially on the water line, has now got tilted. Center of gravity remains the same, but the position of center of buoyancy is going to change because the volume of the submerged portion of the body has changed, and so the point of center of buoyancy would also change, because center of buoyancy is the center of the submerged portion, and since the submerged portion itself has changed, its center will automatically change. So here this was initially the weight and the buoyant force acting at G and B. Now after giving a small angular tilt of theta, automatically B has shifted to B dash, and buoyant force is now going to act from B dash, and when we extend the line of action through FB, we will end up getting metacenter M. So when the body is tilted by an angle theta, center of buoyancy shifts from B to B dash. Okay. Now a couple is created by equal and opposite forces W and FP to counter the angular displacement. So what has happened here is we have given it an angular displacement in this particular direction. Let's say it's been tilted in the clockwise direction, and so the body has two forces acting on it, the weight and the buoyant force, and weight will be equal to buoyant force since the body is floating, and when it is floating, W minus FB, or the net weight of the body, would be 0, and so W is equal to FB. So there are two equal and opposite forces acting on the boat right now. When it was in the stationary position, W and FB were acting along the same straight line, but once it has been tilted, they are parallel forces, equal and opposite parallel forces acting at a distance from each other, and that will create a couple. So W and FB is going to create a couple. If you can actually see these forces, you can understand that the couple created by W and FB will be in the anti-clockwise direction. And so when we have given a clockwise couple, W and FB will give an anti-clockwise couple that will try to bring the body back to its original position. So that is called a restoring couple, and the restoring couple would be given by the force into the distance between the forces. That is the magnitude of the couple, the force into the distance between the forces. And so the force is FB, and the distance between the forces is this particular distance, which can be obtained as Bm sine theta. The distance between the forces, the perpendicular distance between the forces, can be obtained as Bm sine theta. Now since theta is very, very small, sine theta can be approximated to theta, and so the restoring couple would be FB into Bm into theta. Now this is marked as equation number 1. We can keep it aside. Now, the restoring couple that we found out by uh, writing it as FB into BM into theta can also be actually found in a completely different way. What we are doing is we are considering two wedges here, A, O, A dash and C, O, C dash, two different wedges over here, AOA dash and COC dash. So when wedge AOA dash comes out of the water, after when the boat is given a tilt, the wedge AOA dash comes out of the water and the wedge COC dash goes into the water. So when the body is tilted, wedge AOA dash comes out of the water and wedge COC dash goes into the water. So let dA be an elemental area on the wedge. So I'm going to take dA. This is dA. It's a small elemental area on this wedge. Okay. Now I have defined the properties of dA. It is having a width of dx. The angle made by dA is theta and it is at a distance of x from O. Now the same thing dA, whatever dA I've drawn on the wedge A dash will exist in COC dash also. So now dA is equal to, dA is given by x into theta, which is the arc length, into dx. So x theta into dx is the value of dA. So the same thing that I have drawn in wedge AOA dash has come in wedge COC dash also. This is dA, this is theta, this is x and this is dx, the same thing. Now an important phenomena here is that this small dA or this volume corresponding to dA would be subjected to a buoyant force in the upward direction. So here I have drawn buoyant force DFB, which stands for a very small buoyant force that is going to act on the volume submerged corresponding to the area dA. The volume corresponding to area dA would be subjected to a buoyant force DFB. And this is the upward thrust on dA. Now, in the initial case, when the boat was horizontal, the dA on the wedge AOA dash was also subjected to a force DFB. However, when it came out of the water, this DFB has disappeared. That is, this buoyant force will no longer act on this area dA because it has come out of the water. So, in order to show that there is a reduction in buoyant force for this area dA, I will draw DFB in the opposite direction. This is actually a non-existent force. This has been drawn to show that there is a reduction in the upward force acting on the body because the wedge AOA dash has come out. So you have two equal and opposite forces DFB acting at a distance from each other. So they will also create a couple. So the restoring couple produced by DFB would be DFB into 2x. So that is the restoring couple created by the small buoyant force acting on the small elemental area dA. Now, millions of such dAs would be acting throughout the wedge. So in order to find out the total restoring couple by the wedges, we have to integrate. So the total restoring couple would be given by integral of 2x into DFB. Now, DFB would be the weight of the submerged volume dV. That is, there is a volume corresponding to this elemental area dA, and the weight of that submerged volume would be equal to buoyant force DFB. So that is given by volume into density of the fluid into G. So dV into rho liquid into G is the value of DFB. Now, before moving forward, okay, dV has been written as dA into L. L is the length of the boat, which is into the plane of the screen, which is not visible to us. Okay, so the volume of the small element would be dA into L, and so DFB would be dA into L into rho L to G. Now, before moving forward, this is the top view of the boat. Now, this small elemental area dA, I'm going to show you how it would look on the top view of the boat. So from the top view, this is how elemental area, the cross-sectional area dA would look on the top, and the area on the top would be, I have shown it as dA dash. It would be there on both sides of the center line of the board, dA dash. Here, it's at a distance x from the center line. This distance x has been shown here, x and x on either side, just like dA is placed at x and x from O. So if this is the axis YY, then IY is given as 2 times integral x squared dA dash. Now dA dash is given by L into dx. Okay, so this is the basic definition for moment of inertia. Iy is given by 2 times this time, because we are taking YY is the center axis, and if we want to take the moment of inertia of the whole boat about the YY axis, you have to integrate from this side and you have to also integrate from this side. So Iy is 2 times integral x squared dA dash. dA dash is the top top face area of the element dA. So if this element dA was considered as a cuboid, the cross-sectional area would be x theta into dx, which is dA, and the top face area would be L into dx, which is dA dash. So dA dash is given by L into dx. And Iy would be given by 2 times integral x squared into dA dash. This is required before moving forward with the derivation. Now coming back to the restoring couple, which is integral 2x into dfb, total restoring couple, integral 2x into dfb. dfb has been substituted with dA into L into rho L into G. This is, so integral 2x into dA into L into rho liquid into G. This is the total restoring couple. So we'll take the common, constant terms outside, L into rho liquid into G into 2 into integral x into dA can be rewritten as x theta dx. So into x theta dx, but theta is also a constant. So theta can also be brought inside. Now what I'm going to do is I'm going to take theta outside. I'm going to take L inside. And so I will get rho L into G into theta into 2 into integral x squared L dx. Why I have taken L inside is L dx stands for dA dash. And 2 times integral x squared dA dash stands for Iy. And so I can rewrite this equation as rho L times G into theta into 2 into integral x squared dA dash. 2 into x squared dA dash is nothing but Iy. That is moment of inertia about the y-axis. And so I will get the total restoring couple to be rho L into G into theta into Iy. And this has been marked as the second equation. This is also the restoring couple. So what we earlier found out as FB into BM into theta is the same as rho L into G into theta into Iy. So now we will equate the restoring couples, that is equations 1 and 2. FB into BM into theta is equal to rho liquid into G into theta into Iy. Now FB is the buoyant force. We can replace it with the formula for buoyant force. So buoyant force is given by rho liquid into volume of the submerged portion into G. That is the weight of the submerged portion of the boat. That is buoyant force. Into BM into theta is equal to rho liquid into G into theta into Iy. So common terms rho L and G can be cancelled out, and theta can also be cancelled out on both the sides, and so we will end up getting BM is equal to Iy by volume of the submerged portion. BM is equal to Iy by volume of the submerged portion. This is the distance between center of buoyancy and metacenter. Now, like we defined, metacentric height is actually the distance between the metacenter and the center of gravity, that is mg. That is our metacenter. And so there are some cases that we will have to discuss. Case 1 is when center of gravity lies above, metacenter lies above the center of gravity. In this case, we can see that mg, so bm is given by mg plus bg, or I can write mg is given by, or bm can be substituted by Iy by volume of the submerged portion. So bg plus mg is Iy by volume of submerged portion, or mg is equal to Iy by volume of the submerged portion minus bg. This is case 1. This is when metacenter lies above the center of gravity. Now there is another case when the metacenter lies below the center of gravity. In this case, Bm would be given by Bg minus Mg. And so again, Bm is known to us as Iy by volume of the submerged portion. So metacentric height can be written as Bg minus Iy by volume of the submerged portion. So in case 1, Mg is Iy by volume of submerged portion minus Bg. In the second case, Mg is Bg minus Iy by volume of submerged portion. So we can conclude that metacentric height is given by plus or minus Iy by volume of the submerged portion minus Bg. Bg means the distance between center of buoyancy and center of gravity. That is Bg. Okay. So this is case 1 and case 2. Now let's do some numerical problems. A block of specific gravity 0.7 floats in water. Determine the metacentric height of the block if the size of the block is 2 meter by 1 meter by 0.8 meter. So you can directly use the formula. Now you might wonder whether to use Iy by volume of submerged portion minus Bg or Bg minus Iy by volume of submerged portion. How do you know whether it is case 1 or case 2? Doesn't matter. You can simply use the first formula, which is Iy by volume of the submerged portion minus Bg. And if you are getting a negative answer, it would be case 2. So let's move ahead with the problem. And in the problem, they've given us the specific gravity of the block and the dimensions of the block. So the depth of immersion of the block is not given. So like in the previous lecture where we had actually found out the depth of the submerged portion, we will use this information to first find out the depth of the submerged portion, use it to find out the center of buoyancy. Center of gravity is directly located, and then once you know the depth of immersion, you will also be able to know the volume of the submerged portion, and what is left is Iy, and I will explain how Iy is calculated here. So this is the block. Its width is 1 meter and depth is 0.8 meter. Depth of immersion is x, and it's a floating body, and the density of the block is given as 700 kilogram per meter cube. The specific gravity is given as 0.7, so density is 700 kilogram per meter cube. So for determining x, we will use the classic formula for a floating body. W minus Fb is equal to 0, and we'll substitute for the formulas of W and Fb. So W is volume of the block into density of the block into G. Buoyant force is the weight of the water displaced. So volume of the water displaced into density of water into G. So volume of the water displaced can be written in terms of X. Density of water is known. G is known. In fact, G gets cancelled off because it's common. So volume of the block would be 1 into 0.8 into 2. Density of the block is 700. And volume of the water displaced would be 1 into 2 into x, which is 2x, and density of the water is 1000. So cancelling all the common terms, we will end up x is equal to 0.56 meter. So this depth of immersion is known to us. So center of buoyancy can be located at the center, and so buoyancy is at a distance of 0.56 by 2, that is equal to 0.28 meter from the free surface, or you can also say 0.28 meters from the base. Now this is only half of the question. We have only found out the center of buoyancy. We need to find out the metacentric height. So here, center of gravity is located at 0.4 meter from the base because the total depth is 0.8 meter. And center of gravity would be located exactly at the center. So center of gravity is at 0.4 meter and center of buoyancy is at 0.28 meter. So Bg can be found out as 0.4 minus 0.28, that is 0.12 meter. Now, Iy by volume of submerged minus Bg is equal to Mg. So how to find out Iy? Iy is the volume about the y-axis of the body, of the submerged body. So how to draw the y-axis? From the derivation you would remember that this was Yy, and so you have to find out the moment of inertia about this axis, and this is a rectangle, and so it would be 2 into 1 cube by 12. So whichever side the axis is cutting, that side gets cubed when you find out the moment of inertia. So 2 into 1 cube by 12 would be Iyy. So Iyy would be 2 into 1 cube by 12, which is 0.167 meter raised to 4. Volume of the submerged portion is 2 into x, that is 2 into 0.28. Sorry, 2 into 0.56. So that is equal to 1.12 meter cube, and Mg can be written as Iy by volume of the submerged portion minus Bg. And if you substitute the values that you have obtained, we will obtain the metacentric height to be equal to 0.029 meter or 2.9 centimeter. This is the second problem. A rectangular pontoon 5 meter long, 3 meter wide and 1.2 meter high. So the dimensions are given. The depth of immersion of the pontoon is 0.8 meter in seawater. Determine the metacentric height. Density of seawater is 1025 kilogram per meter cube. Here it is a much simpler problem because the depth of immersion is given to us. So volume of the submerged portion can be found out. Position of center of buoyancy can be found out. Position of center of gravity can be easily found out. And Iy is simply the moment of inertia of the top face with respect to the YY axis. So this is an easy problem. This is the three-dimensional figure. 1.2 meter depth, 3 meter width and 5 meter length. This figure can be used to find out Iyy. So this is the YY axis. Iyy would be simply 5 into 3 cube divided by 12, which is 11.25 meter raised to 4. And this depth of immersion is given to us, which means the position of center of buoyancy can be easily found out. Center of buoyancy is 0.4 meter from the base. If you want to find out the center of gravity is 0.6 meter from the base, which is half of 1.2. And so BG would be 0.6 minus 0.4, which is 0.2 meter. Now, metacentric height is given by Iy by volume of the submerged portion minus BG. Now, substituting, Iy is 11.25, volume of the submerged portion is 5 into 3 into 0.8 because the depth of the immersed portion is 0.8 meter. Minus BG has been calculated to be 0.2. And so mg can be obtained as 0.7375 meter. It's a very simple, easy, straightforward question. Now we move on to stability of floating bodies. Here, stability of partially submerged floating bodies. Now, those of you who are hearing this term for the first time might wonder what's the difference between equilibrium and stability. So what is the difference between equilibrium and stability? A body is said to be in equilibrium when the net force acting on it is zero. That everybody knows. An equilibrium can be stable, unstable, or neutral. So basically, stability is not equilibrium. Equilibrium is when the net force is zero, but the same equilibrium can be either stable, unstable, or neutral. Stability of a body is based on the fact that whether it tries to restore its equilibrium when subject to a small angular displacement. That is, when we are providing it with a small angular displacement, will the body try to come back to its original position, or whether the body will overturn, or whether the body will remain where it is. All this gives us the condition of stability. Now we will be looking into more detail about the stability conditions. So this is a partially submerged floating body. As you can see, this is the center of gravity and this is the center of buoyancy. Center of buoyancy is the center of the submerged portion. Center of gravity is the center of the body. Now we are discussing about case 1 stable equilibrium. Now this body is going to be subjected to a small angular displacement. This is the angular displacement given to the body, and the body will tilt. When the body tilts, this is the normal axis of the body, but the center of buoyancy is going to shift because the volume of the submerged portion has changed, and center of buoyancy is the center of the submerged portion. So B has shifted to B dash, and now buoyant force is going to act through B dash, and that is going to give us the metacenter. The point through which the line of action of the buoyant force meets the normal axis is known as metacenter. So this is the metacenter. Now, what is important is that W and FB are going to create a couple because they're equal and opposite. W is equal to FB because it's a floating body, and their parallel forces, equal and opposite parallel forces acting at a distance, so they will create a couple. Now, what type of couple will W and FB create? If you look at it closely, you will understand that it is going to create an anti-clockwise couple. This is the angular displacement and it is given in the clockwise direction, whereas W and FB is going to create a couple in the anti-clockwise direction, that is opposite to the direction of the tilt. So the body is going to try, and this is known as a restoring couple, and the body is going to try and oppose this angular displacement. It is going to try and come back to its original position. So such an equilibrium is known as stable equilibrium. So when M falls above G, you can see the position of M is above center of gravity G. It is noticed that a restoring couple is produced by W and FB. that tries to bring the body back to its original position. Thus, the body is known to be in stable equilibrium. This is known as stable equilibrium. Next, let us discuss about unstable equilibrium. Again, W and FB acting at G and B respectively, the dotted line showing the normal axis. We are going to give the body an angular displacement. The body gets displaced and the center of buoyancy now shifts to a new point B dash because of the change in the volume of the submerged body. Now, if we draw FB to be acting through B dash and extend its line of action, we obtain metacenter M at a point here which is below center of gravity G. Now, if we look at the couple that is going to be created by W and FB, you can see that this time FB falls to the left of W and they're equal and opposite forces, but they're going to create a couple in the clockwise direction. So angular displacement is in the clockwise direction, and in addition to that, W and FB is going to create a clockwise couple. So that means they're going to augment this angular displacement and the body will be going to overturn. So this type of a couple is known as an aiding couple. W and FB here tries to aid the angular displacement and the body tends to overturn. So when M falls below G, a couple is produced by W and FB that tries to push the body along the direction of displacement, making it overturn. Thus, the body is said to be in unstable equilibrium. Now, the third condition or the third case is neutral equilibrium. So this is W and FB acting at G and B respectively. Now we're going to give it an angular displacement. The body is going to tilt. Center of buoyancy is going to shift to B dash. FB is going to act through B dash. But when we extend the line of action of FB, it is found to coincide with the center of gravity. That is, metacenter is going to coincide with the center of gravity. And so W and FB are going to act along the same line. When we give it an angular displacement also, W and FB are going to act along the same line. And because of this, when M coincides with G, no couple is produced. In order for a couple to get produced, equal and opposite forces should have a particular distance between them. But here W and FB are going to act along the same line, and so no couple is created. And so the body does not overturn, neither does the body get restored. The body remains in this tilted position. So the body remains in its new position. It does not get restored and nor does it get overturned. Such an equilibrium is known as neutral equilibrium. So we can understand that for partially submerged bodies, if metacenter is above center of gravity, it is going to be in stable equilibrium. If metacenter is below center of gravity, it is going to be in unstable equilibrium. And if metacenter coincides with center of gravity, it is going to be neutral equilibrium. So the first case, when metacenter is above center of gravity, it's a stable equilibrium case. Mg is given by Bm minus Bg, but we know that Bm is Iy by volume of the submerged portion. So for stable equilibrium, the formula for metacentric height is given by Iy by volume of the submerged portion minus Bg. This is the second case where M is below G, case 2 unstable equilibrium, and Mg here is given by Bg minus Bm, or Mg is given by Bg minus Iy by volume of submerged portion. So if the body is in unstable equilibrium, metacentric height is given by the formula Bg minus Iy by volume of the submerged portion. If it was in stable equilibrium, metacentric height would have been Iy by volume of the submerged portion minus Bg. Case 3 is when metacenter coincides with center of gravity, that is neutral equilibrium, and in this particular case Mg is given to be equal to 0. So how do you understand the stability criteria of a body, or how do you from the metacentric height, how would you be able to comment about the stability of a body? So what we're going to do is, if we are asked to calculate the metacentric height, if we calculate Mg as Iy by volume of the submerged portion minus Bg, this is the formula for case 1, stable equilibrium. And if we get a positive value, it means that our calculation shows that the body is in stable equilibrium. However, when we use the same formula and get a negative value, it means that actual mg is bg minus Iy by volume of the submerged portion and body is in unstable equilibrium. And if we get mg as equal to 0, then the body is said to be in neutral equilibrium. And so we will use the same formula, and depending on whether our answer comes out to be positive, negative or 0, we will term the equilibrium to be stable, unstable or neutral respectively. So let's do a problem. A solid cylinder of diameter 4 meter has a height of 4 meter. Find the metacentric height of the cylinder if specific gravity is equal to 0.6 and it is floating in water with its axis vertical. State whether the equilibrium is stable or unstable. So everything is same according when we have found out the formula for metacentric height. Only thing extra statement here is state whether the equilibrium is stable or unstable. That is the only additional statement over here. That is simple. After finding out metacenter, just look at whether it is positive or negative and comment on whether it is stable or unstable. So let's do this problem. This is the cylinder of diameter 4 meter and height 4 meter. This is the YY axis. Now the YY axis, the top view of the cylinder is a circle. So IYY would be the moment of inertia of a circle about the Y axis, which is pi r raised to 4 by 4. The radius is 2 meter. So pi into 2 raised to 4 by 4, which would give 4 pi meter raised to 4. This is the moment of inertia about the Y axis. Always when you're taking moment of inertia, take it about the face, top face of the body. This is the cross-sectional view. The cross-sectional view, the cylinder looks like a cuboid itself. The height is 4 meter, diameter is 4 meter, depth of immersion is not known to us. We have to find out the depth of immersion using the classic formula W minus FB is equal to 0. So it is given that density of the cylinder is 600 kilogram per meter cube. So to determine X, W minus FB is equal to 0, we're going to substitute for W and FB. Volume of the cylinder into density of the cylinder into G is W. FB is volume of the water displaced into density of water into G. Now volume of a cylinder is given by pi r squared H. So pi r squared H is the volume of the cylinder, and volume of the water displaced would be volume of the immersed portion of the cylinder, which would be pi r squared into X. And so cancelling out all the common terms, we would end up getting X is equal to 2.4 meter, which means center of buoyancy would be at the center, that is 1.2 meter from the base. And thus we would be able to find out the value of BG. G would be at the exact center, which is at 2 meter. So B is at 1.2 meter from the base and G is 2 meters from the base. And so BG can be given as 2 minus 1.2, which is equal to 0.8 meters. So BG can be found out. Now mg is given by Iy by volume of the submerged portion minus bg. Iy has been calculated to be 4 pi meter raised to 4, and volume of the submerged portion is given as pi r squared x, which is pi into 2 squared into x, which is 4 pi x meter cube. X is already known. If you want, you can simply substitute the value of x and find out the value, or you can put it in the fraction and again substitute. So mg is Iy by volume of the submerged portion minus bg. So 4 pi divided by 4 pi into 2.4 minus 0.8, which we will obtain as 0.4167 minus 0.8, which is negative 0.3833 meters. So the metacenter, when we used Iy minus by volume of submerged bg, has been obtained as a negative answer, which shows that body is in unstable equilibrium. So in this next problem, a rectangular wooden block 2 meter long, 1 meter wide and 1 meter deep floats in water. The depth of immersion is 0.75 meter. Find the metacentric height. The specific gravity, that is density of the block, is given. Also asked to comment on stability of the body. So here depth of immersion is given to us, which means our job is half done. We don't have to go through the difficulties of finding out the depth of immersion. And it's a wooden block. It's a rectangular block, so formulas are also very simple. So let's do this problem. So this is the three-dimensional view, 1 meter depth, 1 meter height, and 2 meter length. And this is the cross-sectional view, 1 meter, depth of immersion is 0.75 meter. This is the YY axis. The moment of inertia about the YY axis would be 2 into 1 cube by 12, which is 0.167 meter raised to 4. Center of buoyancy is the half of immersed portion, which is 0.375 meter from the base, and G would be 0.5 meter, that is half of 1 meter, and so BG can be obtained as 0.125 meter, 0.5 minus 0.375. Now mg is given by Iy by volume of the submerged portion minus Bg. So substituting 0.167 divided by 2 into 1 into 0.75, this is the volume of the submerged portion, minus 0.125, which is Bg. We will get negative 0.01367 meter, which means the body is in unstable equilibrium. So earlier we had discussed that there were two methods to determine the metacentric height. One was an analytical method, another was an experimental method. So analytical method has been discussed, and that's where we ended up getting the formula Iy by volume of the submerged portion minus Bg. The next method that we are going to discuss is how to experimentally determine the position or the value of metacentric height. So you can see a boat here, and on top of it a small block of weight small w is placed. We are going to move the small w through a distance x, and because it has moved through a distance x, the boat is going to tilt. Now we are going to use this concept to determine the metacentric height. So in the tilted position, this is the center of gravity, and this was the center of buoyancy of the body. This was the center of gravity, and this was the center of buoyancy initially. Now after the tilt, what happens is center of buoyancy automatically changes position because of the difference in the submerged portion of the body. But so does center of gravity. Center of gravity also shifts in this case because there are two bodies involved here. G is the combined center of gravity of the boat and the small block W. Since the distribution of the mass has shifted, center of gravity will also shift. So this would be B dash, through which buoyant force FB is acting. When you join it to the normal axis, you will get metacenter M, and the angle of tilt is theta. But the most important thing is that center of gravity has also shifted to G dash. And capital W is the weight of the boat plus the weight of the small body is acting through G dash. So here small w is the weight of the block, whereas capital W is the weight of the boat plus weight of the small block. Now this is the small block W, and the weight of the small block W is acting downwards, and it is at a distance of x from the normal axis. Now the components of small block W, the angle made by small block W is theta, because this line is parallel to the normal axis and weight W is parallel to the perpendicular axis. So the angle made by these two lines would be the same angle made between small w and its components. So this is theta, and the components are W cos theta and W sin theta. So if I want to take moment of small w about the normal axis, I would get W cos theta into x. W sin theta will not have any moment about the normal axis because it is going to pass through the normal axis. So moment of small w about the normal axis is W cos theta into x. Now since theta is very, very small, cos theta is approximately equal to 1. And so the moment of small w about the normal axis is nothing but small w into x. This is the first equation. Now shifting W through small distance x, the small block W has shifted through a small distance x. It has resulted in the shifting of center of gravity from G to G dash. Hence, what happens is the total weight acting has shifted from G to G dash. And whenever a force is moved to another point that is not along its line of action, it will be accompanied by a couple. Okay, and that is what I'm going to show you next. And that is the thing that is responsible for creation of this couple is the shifting of the small block, small w. So here, initially W was acting, capital W was acting through G. Now it has shifted to G dash. So when you want to shift a force to a point that does not act along its line of action, then I'm going to draw two capital W cancelling each other at G dash. Now the capital W acting at G downward in the downward direction, the capital W acting at G dash in the upward direction together will form a couple. And so this figure can be equivalent to a small the capital W acting through G dash and a couple equal to capital W into GG dash acting through acting on the body. Now this has happened because the capital W over here and the capital W in the upward direction has created a couple equal to W into GG dash. This happens when a force has to be shifted to another point that is not along its line of action. This has been studied in first year engineering mechanics, and this is just a resultant of that. So when G has shifted from when W has shifted from G to G dash, it has been accompanied by a couple equal to capital W into GG dash. So the couple created due to shifting of capital W from G to G dash is capital W into GG dash. GG dash is nothing but mg sine theta. Sorry, mg tan theta. GG dash is nothing but mg tan theta. Now, the effect of the small block W is the moment about the normal axis as well as the couple created to the capital weight, and the total weight capital W. And so, equating the effects of small w on the whole body, that is equating equations 1 and 2, we will get Wx, which is the moment of small w about the normal axis, is equal to capital W into mg tan theta. Or we will get mg is equal to small wx by capital W tan theta. This is the formula for metacentric height using the experimental method of determination of metacentric height. So this is a numerical problem based on the experimental method. A pontoon of 15,696 kilonewton displacement is floating in water. A weight of 245.25 kilonewton is moved through a distance of 8 meters across the deck of the pontoon, which tilts the pontoon by an angle of 4 degrees. Find the metacentric height of the pontoon. So the answer is this. Small w is given by 245.25 kilonewton, which is 245,250 Newton. Weight of the pontoon, it's given the displacement, but displacement is nothing but the weight because the pontoon is floating. So weight of the pontoon is 15696 kilonewton, which is 156,96000 Newton. X is given as 8 meter, theta is given as 4 degree. It's a direct substitution problem. Capital W is weight of pontoon plus weight of block. So I've added capital W, the weight of pontoon with small w to get capital W, and substituted it in the formula mg is equal to small wx by capital W tan theta, and we obtain 1.76 meter to be the metacentric height. So earlier we had discussed the stability of partially submerged floating bodies. Now we will be discussing the stability of fully submerged floating bodies, that is completely submerged in the fluid. When a body is completely submerged, it does not have a metacenter. Only for partially floating bodies, metacenter is available. So the stability of fully submerged floating bodies is going to be different from the stability of partially submerged floating bodies. So there are three cases for stability, just like partially submerged floating bodies: stable equilibrium, unstable equilibrium, and neutral equilibrium. So let's check out the stable equilibrium. In stable equilibrium, this is the center. Here you can see that center of buoyancy is placed above the center of gravity. This is buoyant force acting in the upward direction and weight acting in the downward direction through center of gravity. Now, when does this happen? Usually, when we have seen, center of buoyancy and center of gravity for fully submerged bodies are coinciding. Center of gravity does not coincide with center of buoyancy if the weight distribution inside the body is not uniform. If the body is more heavier towards the bottom, then center of gravity would be shifting downwards, whereas center of buoyancy would remain at the center. And that is what we can see here. Center of gravity is actually shifted towards the bottom, whereas center of buoyancy is at the center. Now, when we give it an angular displacement, the body will tilt. However, center of buoyancy or center of gravity is not going to shift from its position. You can see that buoyant force and weight are now not acting along the same line, but they're equal and opposite forces that are acting parallel to each other. So they're going to create a couple. And from the figure, we can see that W and FB are going to create an anti-clockwise couple that is going to oppose the given angular displacement. So it will create a restoring couple. And so when center of buoyancy is above center of gravity, a restoring couple is formed by W and FP that will try to restore the position of the body. So you give it an angular displacement, it will try to come back to its original position when B is above G. Hence, the body is said to be in stable equilibrium. When we take the second case, it is unstable equilibrium. Here we can see center of gravity is above center of buoyancy. Now, we will give a small angular displacement to this body and the body is going to shift. Now W and FB are again going to form a couple amongst themselves. However, the direction of this couple is going to be clockwise. That is, it is going to be in the same direction as the given angular displacement, and this is going to create an aiding couple, or it will aid in the overturning of the body. It will aid the angular displacement to overturn the body. So when B falls below G, an aiding couple is formed by W and FP that will overturn the body. Thus, the equilibrium is known as unstable equilibrium. Next case is neutral equilibrium. This is the case for a uniformly mass distributed body. Center of buoyancy and center of gravity fall at the center and they coincide. W and FB will be acting through the same point. Even when tilted, after giving an angular displacement, the position of center of buoyancy and center of gravity is not going to change, and so B will coincide with G and no couple is created because W and FB are going to act along the same straight line. Couple is not produced, and so the body will remain in its new position. Thus, the body will be in neutral equilibrium. When I say the body remains in its new position, it means that after giving the angular displacement, the body has tilted. This body cannot go back to its original position because there is no restoring couple. This body cannot go forward and overturn because there is no aiding couple. So in whatever position the body is in right now, it remains in that position. That is known as neutral equilibrium. So if we take a summary of stability of fully submerged floating bodies, there are three cases for stability of fully submerged floating bodies. Case 1, stable equilibrium is when B is above G. Case 2, unstable equilibrium is when B is below G. In case 3, neutral equilibrium is when B coincides with G. So this was a lecture on the stability of floating bodies. Hopefully you have been able to follow and you will be able to do numerical problems that come from this particular topic. Thank you.